In less than 3 years, you will be able to walk outside on a clear night, look up and see an asteroid moving across the sky with your own eyes. No telescope, no binoculars, no equipment of any kind. Just look up. An asteroid 375 meters wide, wider than the Eiffel Tower, is tall, moving visibly across the night sky. 90% of every human being alive on this planet will be able to see it. The date is already fixed. April 13th, 2029. That is the answer to whether you should be worried. But here is the part nobody is telling you alongside that answer. For 3 weeks in December 2004, the calculations coming back from every major planetary defense group on Earth showed a 2.7% probability that this exact rock would hit us on that exact date. Level 4 on the Torino scale, the scale that runs from 0 to 10, where 10 means certain civilization-ending catastrophe. No asteroid in modern history had ever reached level 4. Apophis reached it. And buried inside that probability was something worse. A region of space 800 meters wide, smaller than most airport runways that Apophis might thread during the flyby, causing Earth's own gravity to bend its path and set up a guaranteed second strike 7 years later. The threat was real, the fear was justified, and it was resolved on December 27, 2004, by one astronomer who found photographs that nobody had looked at yet. This is that full story, what Apophis is, what it will do in 2029, what 2 spacecraft already in transit are going to find when they get there, and why the most important discovery from this encounter may not be about Apophis at all, but about every other asteroid we are not yet watching. New here, I cover what is actually happening in space right now, with real numbers and real stakes. Subscribe. You will not want to miss what comes next. The astronomer who broke the fear was Jeff Larson. On December 27, 2004, Larson and colleagues working with the Spacewatch Sky Survey at Kitt Peak in Arizona dug through photographic archives and found images of the same object taken on March 15, 2004, 9 months before anyone knew to look for it. In astronomy, this is called a pre-discovery. It matters because the precision of any orbital calculation depends entirely on how long a baseline of observations you have. The longer the stretch of time between your oldest and newest data points, the tighter and more accurate your orbit. Adding 9 months of additional baseline to the Apophis calculation changed the answer immediately. The impact probability collapsed to essentially 0. The 800-meter keyhole scenario, the guaranteed second strike, went with it. And the asteroid, which had been given its permanent name by then, became something different from what it had been for 3 terrifying weeks. The name was Apophis, taken from the ancient Egyptian serpent, deity of chaos, the enemy of order and light. Given in December 2004, when nobody was certain it was not going to hit us, it earned the name, and then it was confirmed safe. And the story, which should have ended there, turned into something else entirely. Because what replaced the fear was an opportunity that planetary science had never been handed before. Here is what Apophis is going to do on April 13th, 2029, a Friday, and why it matters. It will pass within 32,000 kilometers of Earth's surface. To understand what that distance means, the ring of satellites that orbit Earth at geosynchronous altitude, the communication satellites, the weather satellites, the GPS infrastructure sits at approximately 36,000 kilometers. Apophis will pass inside that ring. An asteroid 375 meters wide will briefly be deeper in Earth's gravitational field than most of our own satellites. Events of this scale, an object this large coming this close, happen on timescales of 5,000 to 10,000 years. The previous time something comparable occurred, written records did not exist. The next comparable event after 2029 will likely occur after anything resembling our current civilization has ended. And for the first time in the history of our species, we knew about it years in advance. We have instruments ready. We have 2 spacecraft already in transit. Up to 90% of Earth's population will be able to see it with the naked eye. No telescope, no binoculars, a steady point of light moving visibly across the sky, shining as brightly as the stars of the Big Dipper, crossing from horizon to horizon over several hours. 2 billion people in Europe, Africa, and Western Asia will have the best view. Richard Binzel, the MIT planetary scientist who created the Torino scale in 1999 and who opened the June 2026 Apophis workshop at the University of Padua, said it plainly: Apophis will safely pass the Earth. He said it 3 times, by several accounts, not because the audience needed convincing of the physics, because the name of the asteroid and the history of 2004 made it necessary to establish the ground truth clearly before discussing what the flyby actually is. What it actually is a once-per-millennium natural experiment, And here is what makes it genuinely extraordinary, not just as a spectacle, but as science. Nobody has ever watched an asteroid get stress tested by Earth's gravity from alongside the asteroid. We have studied asteroids from Earth. We have sent spacecraft to them, Hayabusa and Hayabusa 2 to Itokawa and Ryugu, New Horizons past Arrokoth beyond Pluto, OSIRIS-REx to Bennu. We know a great deal about what asteroids look like from the outside, and in some cases, what their surfaces feel like at a single contact point. But we have never positioned instruments to watch a large asteroid as Earth's gravity reshapes it in real time. We have never had the before and after dataset. We have never been able to observe how tidal forces, the same mechanism that generates ocean tides on Earth, change an asteroid's rotation, internal structure, and surface stability across a single close encounter. 2029 gives us that. And to understand why the encounter is so scientifically rich, you need to understand what Apophis actually is, because the answer is considerably stranger than a smooth sphere of rock. Start with the shape. Radar measurements using a technique called delay Doppler imaging, bouncing radio signals off the asteroid and measuring both the travel time of the echoes and how their frequency shifts as the asteroid rotates, have produced a silhouette that looks like two mismatched stones fused at a narrow neck, two lobes connected at a pinched middle, like a cosmic peanut. The same structure appears in Itokawa, which Hayabusa physically touched, and in Arrokoth, the distant object New Horizons photographed beyond Pluto. If Apophis has this structure, it is not one rock, it is two rocks, held together at a narrow contact point by nothing stronger than their own mutual gravity. A body like that does not respond to external forces the way a solid sphere would. And in 2029, Apophis is going to be subjected to the strongest external force it has experienced in a very long time. Then there is the rotation, which adds the layer of complexity that makes the 2029 encounter genuinely unpredictable in its details. Most asteroids spin cleanly around one stable axis. Apophis does not. It tumbles. Instead of a steady rotation, it wobbles simultaneously around more than one axis at the same time, cycling through a complicated loop rather than repeating the same turn. Physicists call this non-principal axis rotation. Three separate rhythms run at the same time, a long cycle of approximately 264 hours, a shorter cycle of roughly 27 hours, and an underlying rotation period near 31 hours. All three unsynchronized. All three simultaneous. Something knocked Apophis into this tumble at some point in the past. An old collision, an uneven internal mass, or a previous planetary encounter. Once a small body begins that kind of wobble, there is typically nothing internal strong enough to dampen it back out. The tumble can persist for millions of years. In 2029, Earth's gravity is going to grab that already unstable tumble and pull on it. The side of Apophis facing Earth during closest approach gets tugged toward our planet more strongly than the far side. That imbalance, the same mechanism that raises ocean tides, creates a stretching and squeezing force across the entire body. Research presented at the Padua workshop predicts the tidal interaction could dramatically alter Apophis's existing tumble, with its effective spin rate potentially halving or doubling, and its rotation axis shifting by 10 degrees or more. Joe DiMartini, a postdoctoral researcher at the University of Helsinki who presented at the Padua workshop, put it with remarkable simplicity. Earth provides the experiment for us. All we have to do is put an instrument there. That sentence is worth pausing on. For the first time in the history of planetary science, Earth itself is conducting the experiment. Not a spacecraft, not a laboratory. Our own planet's gravity is the instrument. And all scientists have to do is position themselves to watch. So what does it take to watch? And why does it require two spacecraft already in transit? Here is where this story goes. Somewhere the headlines never reached. The person leading NASA's Apophis mission is Dani Mendoza DellaGiustina, a planetary scientist at the University of Arizona, who spent 7 years working on OSIRIS-REx, the mission that orbited Bennu, collected a sample, and delivered it safely to Earth in September 2023. After a successful sample return after 7 years of work completed, the spacecraft had fuel remaining. DellaGiustina convinced NASA to keep it running. The mission was renamed OSIRIS-APEX, and the spacecraft that spent years studying one asteroid turned around and started chasing a second one. On November 25, 2025, OSIRIS-APEX performed a gravity assist. It flew past Earth, using our own planet's gravity to redirect itself toward Apophis. The spacecraft sampled Bennu, came home, dropped the sample, then swung past Earth again on its way to its next target. It will arrive at Apophis on June 5th, 2029, approximately 2 months after closest approach, and begin an 18-month campaign to study the aftermath of what Earth's gravity did. One of its most distinctive planned activities involves firing its thrusters directly at the asteroid's surface, from close range, not to damage anything, but to kick up loose material and reveal what sits just below the outer layer. The same technique was tested at Bennu, where the sample collection attempt revealed a surface so weakly bound that the spacecraft nearly disappeared into it. A direct physical confirmation that Bennu was a rubble pile loosely packed rock, held together by gravity alone. The same question is open for Apophis, and the tidal forces of the 2029 flyby will already have reshaped whatever loose material sits on the surface before OSIRIS-APEX arrives to look. The before picture comes from Europe. ESA's RAMSES mission, the Rapid Apophis mission for space safety, is a joint program with Japan's JAXA signed in formal agreement on May 7, 2026. The prime contract went to OHB Italia. RAMSES launches in April 2028, arrives at Apophis in February 2029, 2 months before closest approach, and then stays with the asteroid through the entire flyby and beyond, matching its speed and following alongside it the way two cars travel the same road. RAMSES carries a CubeSat named Farinella after Paolo Farinella, the Italian planetary scientist who formalized the concept of asteroid families and whose work underpins everything modern science knows about rubble pile asteroids. Farinella, the CubeSat, carries a low-frequency radar that will penetrate beneath Apophis's surface and map its interior structure directly. We have never seen inside a rubble pile asteroid. Nobody knows whether the interior is a loose aggregate of rock held together by gravity alone, or whether it conceals a larger coherent mass at its center. The Farinella radar will answer that. Line the missions together, and what exists is unprecedented. RAMSES arrives early, measures everything about Apophis as it exists before Earth's gravity touches it. The flyby happens. Earth's gravity stress tests the body in real time, while ground telescopes around the planet watch. OSIRIS-APEX arrives in the aftermath, maps the changed surface, fires its thrusters into the altered regolith, and studies the longer-term effects for 18 months. Before, during, after, from alongside, from the surface, from the interior. The most comprehensively instrumented asteroid encounter ever planned, and nature designed the entire experiment. All science had to do was show up. So, should we be worried? No. The answer is unambiguous, and it has been unambiguous since December 27, 2004. The orbital uncertainty code for Apophis now sits at 0, the most confident designation the tracking system awards. The probability of impact on April 13, 2029 is 0. NASA's Sentry Impact Monitoring System formally removed it from the risk table after the 2021 radar campaign confirmed the orbit to a precision that rules out any possibility of Earth impact for at least the next 100 years. The Torino scale level 4 that made December 2004 a genuinely frightening month is a historical footnote. Richard Binzel created that scale. He watched Apophis reach it. He watched it come back down. He stood at the Padua workshop in June 2026 and said it 3 times, not because the science required it, but because some things are worth saying clearly. Apophis will safely pass the Earth. What it will not do is pass quietly. On April 13th, 2029, a Friday, 90% of the humans alive on this planet will be able to look up and see a rock the size of a cruise liner moving across the sky with their own eyes. 2 spacecraft will be watching from alongside it. A CubeSat named for the scientist who taught us how asteroids are built will be looking inside it. And whatever Earth's gravity does to its tumble, its surface, and its interior during those 7 hours will be observed, measured, and publish the first complete before and after dataset in the history of planetary science. The god of chaos arrives on schedule, and this time, instead of dreading it, the entire planet is ready to watch.